All right, well, welcome back, and let's take a look this week at our lab on the Hawaiian Islands and the Emperor Seamounts. Very fascinating part of our world, and we get to understand it from a deeper lens, no pun intended, with our tools in physical geography, some of this spanning into physical geology, and one could make a case for volcanology as well. And it continues on our theme of plate tectonics, and we dive a little bit deeper to look at hotspot theory in particular. So the vast majority of earthquakes and volcanic activity occur near plate boundaries. We looked at that, some of those plate boundaries last week, and we'll continue to. However, there are exceptions known as intraplate volcanism that are far from the plate margins, with the Hawaiian Islands being a great example of those. So in 1963, Canadian geophysicist J. Tuzo Wilson hypothesized the distinctive linear shape of the Hawaiian Island Emperor Seamounts chain resulted from the Pacific Plate moving over a deep stationary plume in the mantle. And so again, we get to refresh some of our key geological terms out of physical geography lecture that we learned about, plume and mantle. But where I'm going with this is that such spots are known as a hot spot, because it's literally one particular spot burning a hole up through the crust, or melting a hole up through, if you will. But to continue on that thread, have a little bit more about these stationary mantle plumes for you, which is a different way to think of a hotspot. That is as a stationary mantle plume. A bit longer, cumbersome of a phrase. These are an important feature of mantle convection, as they produce surface volcanism that is not necessarily associated with plate boundaries. So a little bit of what we were referring to on the last slide there, but it speaks to their uniqueness, just highlighting that they are not near plate boundaries. There are numerous plumes of different sizes scattered around the globe. Some are associated with chains of islands and seamounts, and others are currently burning through continental crust. And some prime examples of those are Yellowstone and some of the volcanism that we know of from there, including geysers. And then also, a little closer to home, the Long Valley caldera on the east side of the Sierra Nevada of California. A phenomenal area of this world as well. One of my favorite parts of the state of California, and just a geologic, physical, geographic wonder world to go explore when you get a chance. Hot springs and the Sierra Nevada rising, practically straight out of the earth right there. Its eastern face steep and majestic. The White Mountains to the east, looking out over the Long Valley caldera, the bristlecone pines. Couldn't recommend it enough when you get a chance. Perhaps some of you have already been there, skied at Mammoth, or hit up Crab Cooker Hot Spring. Just a beautiful part. And so that's my little rant about the Long Valley caldera for you. So to continue here about the stationary mantle plumes and hotspots, perhaps the most famous in the world is Kilauea, it's also the most active volcano in Hawaii, and owes its existence to the very active hotspot, which is currently located on the southeast coast of the quote-unquote Big Island of Hawaii. And a stunning picture there of the molten lava crater. The Hawaiian Island and Emperor Seamounts, to elaborate a little bit more on why we're including the Emperor Seamounts with the Hawaiian Island chain here. I could pluralize that islands, but Hawaii is part of an extensive chain of islands and submarine volcanic peaks known as seamounts. Those submarine volcanic peaks in particular are known as seamounts. The Hawaiian Island Emperor chain of volcanic islands and seamounts stretches almost 6,000 kilometers across the floor of the Pacific Ocean. That's staggering. It's 6 times 0.6. It's over 3,500 miles. So it's as wide as as the continental U.S., if not a little wider. Some of these distances are really exciting to think about, this chain of islands, seamounts. The age of the seamounts become progressively older and more eroded as distance increases from the active Mantle plume, which we know is on the Big Island, and even a little bit further south from that. And here, this diagram shows us what we're referring to. Classic picture is worth 1,000 words. So starting off on the Earth or the globe view here, we see the Hawaiian Islands, and actually this large expanse, here's Hawaii, and the Hawaiian chain extends much further than Kauai. And then this northern part is the Emperor Seamount chain. And so that 6,000 kilometers would be from the northern end of the Emperor Seamount, almost close to the Aleutian Trench up there in the Aleutian Islands, getting quite close to Kamchatka Peninsula as well of Russia. And so it just almost spans the extent of the North Pacific. Just this phenomenal distance across the ocean there. It's mind-blowing. And here you see on the background image, direction of plate motion. See how with one central place here, the Mantle plume, one spot, and the Pacific plate moving northwest over it, it leaves these successive islands, seamounts. Islands which then, we could call them volcanoes, which form islands, which then move further away from the Mantle plume, the hot spot, and they erode and sink back under sea surface. And that's why they're just seamounts. With some different ages here of ages given in millions of years. So Kauai at 3.8 to 5.6 millions of years, with the youngest being Hawaii at 0.7. So 700,000 years until the present. Quite young compared to some of these other islands, and the seamounts being even older. And here what I referred to briefly there, the newest Hawaiian island, as the Pacific plate continues to move northwest, the island of Hawaii will be carried beyond the hot spot by plate motion. In time, a new volcanic island will emerge southeast of the Big Island. And in fact, an active submarine volcano is already forming about 35 kilometers off the south coast of Hawaii. And assuming that Loihi continues to grow, it will become the next island in the chain, joining this fine lineage of beautiful Hawaiian islands. The seamount, known as Loihi, is, if I'm pronouncing that correctly, if not, my apologies, has risen about 3 kilometers above the ocean floor within 1 kilometer of the ocean surface. So it's 3/4 of the way there. And you see a map here of the Big Island, and then just, I think, 35 kilometers off the coast is Loihi. So pretty neat that not only can we see the history of other islands, but we see, almost the future, so to speak. The next one to come. And here you see more of the Google Earth view of the Hawaiian seamount chain, ranging far beyond the Hawaiian Islands. We were referring to that a little bit earlier as well. And then this point known as the Bend, where this northwest trajectory then turns quite due north. And let you all ponder a little bit. If these are all stemming from the same hotspot, why would there be such a bend, such an arc in the chain there? Why do you think that would be? Okay, so the bend, to dive into it a little bit, at about the time that Daikakuchi, imagine this is a nice Japanese word, especially the Daikakuchi. At the time that it was volcanically active, some 42 million years ago, wow, the direction of the Pacific Plate changed course. This Pacific Plate has been drifting west-northwest direction for about 42 million years. Previous to that, the Pacific Plate was drifting north. So one of the questions that we're going to address this week in lab was the rate at which the Pacific Plate drifted different prior to 42 million years ago compared to the average rate of drift since then.